problem when you Xerox 50 pages of something or other. You know, that I can arrange to do that upstairs.
That might be what I'll have to do. And they're kind of long, so I didn't want to have to photocopy them myself.
Yeah.
But, I mean, because it'll get expensive quickly, like a 100-page article is not.
Yeah.
You know what I mean?
Yeah. Well, that's why I offered that. I don't offer to do physical labor.
I understand. I don't mind the physical labor
but
so
I can
much.
set it up so that
that's the $10
it
I
gets
have to
done,
pay.
2 pages per or something.
Right.
Like that, you know, whatever.
Thank you.
So last time I finished proving this very nice theorem that a Coxeter system is finite if and only if the associated bilinear form is positive definite. And this took the heaviest machinery that we're going to see, that we're going to use in this class. And from now on, it's going to be basically linear algebra. Because what we're going to do is understand which bilinear forms are positive definite. Okay? And so today, what we're going to do is today's class is linear algebra, so it's going to be just talking about positive definiteness. Okay. So let's see, so we have some symmetric bilinear form. Which, let me call it b of x, y for now, just to distinguish it from this one. So just some general symmetric bilinear form, okay? So that means that it's linear in both variables, so it's symmetric, so b of x, y equals b of yx. And from this, we're going to consider the things of the form b of x, x, okay? And I'm going to call this the quadratic form associated to the symmetric bilinear form. Okay? And so my bilinear form is positive definite by definition if my quadratic form is positive for all non-zero x. Okay. So maybe the first thing that's a little bit strange about this is that we're talking about this bilinear form, and positive definiteness only depends on the quadratic form, only on the things of the form b of x comma x. Okay. Now the first thing I'd like to point out to you is that actually this is not so strange, in the sense that actually, if I give you the quadratic form, then you can actually recover the whole bilinear form. So if I tell you what b of x, x is, then you can figure out what b of x, y is for any x and y. So this is a two-way arrow. And it's very simple, actually, because how does this work? Well, the thing is, if you would like to know what b of x, y is, well, I claim that what you have to do is the following. So assuming that you know b of something, comma, that same thing, you want to compute something of this form. Well, the way you can do that is that if you compute what b of x plus y and x plus y is. Okay? This is bilinear, so that means that this is equal to b of xx plus b of xy plus b of yx plus b of yy. Okay? And if you know the quadratic form, that means that you know this, and you know this. And I'm telling you that the bilinear form is symmetric, which means that you know that these guys are equal to each other. And that means you know what b of xy is. It's a half of b of x plus y minus b of xx minus b of yy. So So that's how you get from the quadratic form to the bilinear form, the whole bilinear form. Okay. Now, we talked about how any bilinear form has something called a representing matrix, right? So we can write our bilinear form as, if we choose a basis for our space, then this is just going to be given by X transpose A Y, where this thing is called the representing matrix. Okay. Now, maybe what I'd like to do is make this very concrete today. So I would actually like to show for you an example of a positive definite form. Okay. What do these things look like when I think about them in this way? Now, let me just make a definition that a matrix, a symmetric matrix, A is positive definite basically if this associated bilinear form is positive definite. So if this is positive for all x different from 0. Okay. So I'm making the same definition, but here it's in terms of the bilinear form, and here it's in terms of the matrix. So what's an example of, let's take some matrix. Here's a very simple matrix. Okay. And let's figure out if this thing is positive definite or not. Well, what you do is basically that you have to compute something like this, right? And so what does this look like? Well, we have to compute X transpose AX. So let's say that X is UV. So we get this, okay? And we just have to compute this and see if it's positive or not. So you just go ahead and multiply. So here you get U plus V, okay? And so then you get U times U plus V times U plus V. So you get this. Okay? So is this positive definite? To think about it carefully, because this is supposed to be strictly positive for x non-zero. Okay, this is not strictly positive. It could be 0. So this is 0 for things of the form u minus u, and so this is actually not positive definite. Okay. So when is a matrix like this positive definite? Let's figure out for 2 by 2 matrices when they're positive definite and when they're not. Okay? So this one is not. When is this positive definite? Now, why are these B's and B's? Because we're going to be talking about symmetric things all of today. Okay? So what do you get when you multiply X transpose AX? Well, you get UV times AB BC times UV. And you just multiply this out, and I'll tell you what you get. You get AU squared plus 2B UV plus CV squared. This is what you get. Now, you'll notice by looking at this why I was calling this a quadratic form, because it's quadratic. Some quadratic expression in my vector. So how do I figure out if this is positive or not? Well, the the usual thing is to complete the square. So I get A times U plus B over AV squared. So that gives me the AU squared. It gives me the 2BUV. I have an excess of B squared over AV squared plus CV squared. I get this. And so this is equal to A times U plus B over AV squared plus C minus B squared over AV squared. And the question is, when is it true that this is always positive no matter what my choices of U and V are, except that I shouldn't choose both 0, because if they're both 0, then this is 0. Well, then you see that if you want this to always be positive for any choices of U and V, then what you need is, this expression and this U plus B over AV, and V can take arbitrary values. And so what you need is basically for this coefficient to be positive and this coefficient to be positive. They can't be 0, because, for example, if this one is 0, then you would get something like this, which can be equal to 0 for U and V non-zero. But if you make this one positive and this one positive, then for this thing to be 0, you would need U plus B over AV to be 0, you would need V to be 0, and that would force U and V to both be 0. So this is positive definite if and only if A is positive, and let me multiply by A, which I know is positive now. So A and AC minus B squared are positive. And what I would like to do today is basically develop some tools so that we can deal with this question not only for 2x2 matrices, which we just fully answered, but for arbitrary matrices. How do you settle whether they're positive definite or not? Okay. Any questions about this computation? Is that good? Well, I'm going to use a lemma, but before I use this lemma, let me remind you of something that we have talked about. So this is either a reminder or something that you should prove for yourself if you haven't seen it before. Reminder or exercise. If you have a symmetric matrix, then you can diagonalize it. And you can diagonalize it by a matrix which is orthogonal, meaning that U transpose is equal to U inverse. Okay? So if, let me say this in an equivalent way, which is going to be maybe clearer and easier. So if you have a symmetric matrix, then there's basically a basis of eigenvectors. Okay, so there are linearly, well, there are eigenvectors like this, which are actually orthonormal. Okay? And so when you think about it in this way, it just says basically what your multiplication by A does if you choose the correct basis. Your basis is V1 up to Vn. Then it just stretches the vector V1 by lambda 1, it stretches the vector V2 by lambda 2, etc. And, by the way, these vectors are actually an orthonormal basis. So they're pairwise perpendicular, and they have length 1. Meaning symmetric matrices just are beautiful when it comes to eigenvalues and eigenvectors. Everything goes as well as possible. Okay? So this is the spectral theorem, basically. And I mean this. If you remember this, good, and you should remind yourself how to prove it. And if you don't remember this, this is really a very reasonable linear algebra exercise that you should do. Okay. So you'll go and do that exercise tonight, but even before you have done that exercise, it just means basically that symmetric matrices have very nice eigenvalues and eigenvectors. So here's lemma. A symmetric matrix A is positive definite if and only if all of these lambdas are positive. So I can characterize positive definiteness very nicely in terms of eigenvalues. I just have to check, compute them, and see that they're positive. Okay. So how do we prove this? Well, first let's suppose that A is positive definite. Okay. So that means that V transpose A V is positive for all V non-zero. Okay. In particular, let's plug in one of these eigenvectors. Okay. So let me just plug in Bi here. They're eigenvectors, so they're non-zero. What does that mean? Well, this means that AVI is just lambda IVI. So what I get is VI transpose. Lambda I is a number which I can pull to the front, and VI is bigger than 0. Okay. And now this is just the length of VI, so it's positive. So that means that the eigenvalue is positive. Okay. Easy. How do I go back? Well, let's assume that let's assume that the lambdas are positive. And now let's compute V transpose AV for an arbitrary V. But it's going to be convenient if I write V in terms of that nice orthonormal basis. So what do I get when I compute this? Well, I get C1 V1 plus Cn Vn transposed A C1 Vn up to Cn Vn. Okay, and let's figure out what this is. Basically, I'm going to get two kinds of terms. I'm going to get the terms where when I multiply this out, I'm going to get some terms where it's Vi transpose Vj, and some terms where I get Vi transpose Vi. These are the two kinds of things that I'm going to get. So for example, what do I get with Vi transpose Vi? Well, for example, I get C1 V1 transpose A C1 V1. And in general, I get CIVI transpose A CIVI from I equals 1 to n. Okay? And then I get the things with I different from j, where I pick up CIVI transpose A CJ Vj. Okay? Sorry, this is plus. Okay. Now let me fiddle with this a little bit. So I pull out the CI squared, Okay? And I get VI transpose AVI. Okay? But AVI is lambda IVI. So that means I get lambda I VI transpose VI. Plus, then I do the same thing for I different from J. And what I get is a CI CJ. Then AVJ is lambda J. And then I get VI transpose VJ. Okay? But now we look at this and we say, okay, so first of all, I mean, the main point is that the VIs are an orthonormal basis, which means that if you take VI transpose VJ for I different from J, then you're going to get 0, because VI and VJ are orthogonal. So this is 0. VI transpose VI is 1 because it's the length of VI, and this is an orthonormal basis. And so what I'm going to get is the summation from I equals 1 to n of lambda I Ci squared. And all you see there are positive numbers, because I'm assuming that the eigenvalues are positive. So all of these guys are positive. The Ci squareds, well, at least one of them is going to be positive. And so we get that this number is positive. Which is what we wanted to show. We wanted to show that V transpose AV was positive. So there you go. That's my characterization in terms of eigenvalues. Now let me prove a different characterization. A symmetric matrix A is positive definite if and only if all its principal minors are positive. So of course I need to tell you what a principal minor is, and it's very simple. If you have some square matrix like this, then a principal minor is just a minor that is stuck in the top corner. Okay? So it's any minor like this. Take some square matrix of size k, and you just compute the determinant of this thing. These are the principal minors. Okay. So how many principal minors do I have? Well, you only have one choice here, which is the value of k. Right? K could be anything from 1 up to n. And so that means you have to check the 1 by 1 minor, the 2 by 2 minor, the 3 by 3 minor, until the n by n minor. There's n numbers that you have to check. Okay. Now, if you look at what I have in the little square right here, you'll see that it's exactly the proof of this statement for 2 by 2 matrices. Yeah? I'm trying to figure out if this matrix is positive definite. And what did I prove? I proved that it's positive definite if and only if A and AC minus B squared are positive. But if you look at these things, A is the 1 by 1 minor, 1 by 1 principal minor, and AC minus B squared is the 2 by 2 minor. So that's cute. And that means that this is true for any value of n. So this is due to Sylvester. How do you discover something like this? I don't know. Maybe if you do the 2 by 2 case, you guessed in very wishful thinking that it's true for any n. You maybe think that you're wrong. It turns out that in this case you're right. So this really characterizes it for any size of a square matrix. Okay. So this is a good example of this. Okay. So how are we going to do this? We're going to do this by induction on the size of the matrix. Okay. So what's our first case? N equals 1. You have a matrix that only has one entry, A. So what's the quadratic form? The quadratic form looks like X transpose times matrix times X, right? And this is AU squared, and you would like this to be positive for any value of U that is not 0. And so this is going to be positive if and only if A is positive. Okay. So this is positive for U different from 0 if and only if A is positive and A is the only principal minor of this thing. So it's true for n equals 1. Maybe a more interesting initial case is n equals 2 here, which we already proved. Okay. And now let's suppose this is true for n minus 1 by n minus 1 matrices. And let's prove it for n by n matrices. So, one direction. Suppose that A is positive definite. Okay. A is some matrix that looks like this. Now you see, for my next step, it's kind of clear what I need to do because this is supposed to be an inductive proof. So I somehow want to use the n minus 1 by n minus 1 case, and I don't see any n minus 1 by n minus 1 matrices here, so I better make one. And if I force you to make an n minus 1 by n minus 1 matrix out of this, I think your first guess will be to just chop off the last row and the last column. Okay. So let's call this n minus 1 by n minus 1 matrix A prime. Okay. So what's my next step? Well, it's also kind of clear because this is supposed to be an inductive proof where I'm going to use the matrix A prime. But if I want to use the matrix A prime, then the matrix A prime better satisfy this hypothesis also. That is positive definite. Otherwise, I'm empty-handed here. So the next thing must be to prove that this A prime is positive definite. So let's do that. Well, I need to take some vector of size n minus 1 multiplied by my matrix A prime, and so I need to do this, right, for some V prime transpose of size n minus 1, and I need to prove that this is positive. What is the only thing that I have? My only hypothesis is that A is positive definite. Okay, which means that when the matrix in the middle is A, this is positive. And so I somehow have to go from the statement for A to the statement for A prime. And so the natural way to do that is to rewrite this thing as a similar expression where instead of having A prime in the middle, I have A. Okay. So if I want A here, then what I need is to add my extra row and my extra column that I don't have here. Okay. So now this is an m by n matrix. This is an m by n matrix, so that means that I can't multiply it by this n minus 1 thing anymore, and by this n minus 1 thing. If I want to multiply it, I have to lengthen this guy also, and this guy also, making it of length n. Okay. And do I put it at the top or at the bottom, the last entry? Well, since I added a last column, I should add a last element here. Since I added a last row, I should add a last element here. Okay. I'm trying to make these things equal to each other. And so I should probably be putting a v prime here. I should probably be putting a v prime here. I have no control over what's here, right? Because this is meant to be the matrix A, and I don't get to choose A. A was fed to me ahead of time. The only freedom that I have is what to put in this last entry. What would you put? 0. And then you would pray that this identity is actually true. Right? And it is. It is. You just compute, and basically the effect of having this 0 is that this 0 kills whatever happened with this last column, and this 0 kills whatever happens with this last row. And so these things are actually equal to each other. By the induction hypothesis, sorry, no, by the assumption, A is positive definite, so this is positive, and that means that this is positive definite. Okay. So that's good. Let's see, can I erase this? Maybe not yet. Let's go over here. I like this proof. It's one of these proofs where once you've decided that you're going to do it by induction, then the proof kind of happens, and you just let it happen. So what next? Okay, well, A is positive definite. Then we made this matrix A prime. We just proved that it's positive definite. That means we can apply the induction hypothesis, which says that the principal minors of A prime are positive definite. So by the induction hypothesis, here we have A, then here we have A prime, and by the induction hypothesis, all the minors of A prime are positive. So what are the principal minors of A prime? Well, it's this one, it's this one, it's this one, etc., until this one. All of these guys are positive. So if I want to check that the minors of A are positive, I'm almost done. The last thing I need to do is just check that the last minor is positive. So I just need to check that the last minor, which is just the determinant of A, is positive. And why is that? Well, what did I just erase here? I said a matrix is positive definite if and only if all of its eigenvalues are positive. And how do you compute the determinant in terms of the eigenvalues? The determinant is just the product of the eigenvalues. And I just proved that all of these are positive, which means that the product is positive. So that proves my first direction. Okay. How about the other direction? So let's assume that the principal minors of A are positive. Okay. And what I'm going to try to do is just reverse what I did. Again, I want to induct, so that means I need an n by 1 minus n by 1 matrix. Sorry, n minus 1 by n minus 1 matrix, which is going to be A prime. And of course, the principal minors of A prime are positive. Okay. What does that mean? Well, by the induction hypothesis, that means that A prime is positive definite. Okay. And now somehow I have to go from A prime being positive definite to concluding that A is positive definite, which sounds similar to that, but trickier, right? What do I know? I know that anything that looks like this is positive for V prime non-zero. And I want to translate this into a statement about A, because I want A to be positive definite. And so I'm just going to use that identity that I proved over there. Well, I didn't prove it, but it's very easy to prove. That if you add a 0 here, if you add a 0 here, and you add the last row and column of A here, this is the same number, positive. Okay. So let's call U the set of vectors in Rn of the form something, comma, 0. So U consists of the column vectors in Rn such that the last coordinate is 0. And so, of course, this is a subspace of Rn. Okay. And what did I prove? Well, I proved that if U is in big U, then U transpose A U is positive. If U is in big U and it's not 0, then U transpose A U is positive. Okay. Now, I would like this statement to be true for all of Rn, but this is a reasonably good step. We proved it for a subspace of dimension n minus 1. But we're not done. So what am I going to do now? Well, let's consider the eigenvectors and eigenvalues of A, and let's call them V1 up to Vk. I mean, I'm calling them the same thing as before. Lambda 1, lambda k plus 1 up to lambda n. But the only thing is that I'm labeling them in such a way that the first k are less than or equal to 0, and the last n minus k are bigger than 0. What am I trying to do? Well, I'm trying to prove that A is positive definite. And that's equivalent to saying that all the eigenvalues are positive. In other words, what I really am after is I would like to prove that k is really 0, that there aren't any of these guys. But I don't know that yet because I don't know yet that A is positive definite. Okay. Now, let me define another subspace of Rn we call it V, to be the span of these guys. Okay. Why do I want to do this? Because well, I want to prove the following. I want to prove that if V is in V and V is not 0, then V transpose AV is actually not, it's not positive, it's actually negative. Actually, this is true for 0 also. If V is in V, I'm going to prove that V transpose AV is non-positive. Okay? And this I basically proved already, because I just write V as C1 V1 up to CK VK. And so V transpose AV is nothing but sum of CI VI transpose times A times sum of CI VI. Okay? I'm making the same argument that I made already, that now here's the left thing, CI VI transpose. And what is this? Well, remember, AVI is lambda I. And so this is just CI lambda I VI. Okay, CI is a constant, and A times VI is lambda I VI. And then I make the reasoning again that the VIs are orthonormal, which means that whenever I have a VI transpose VJ, that's going to disappear. I mean, these are numbers, right? CI and CI lambda I are numbers. If I have a VI transpose VJ, that's going to disappear. And if I have a VI transpose VI, that's going to be 1. And so what's going to be left here is just the terms for I equal to I here. I'm going to get CI squared lambda I. CI squared is positive, and the lambda i's are less than or equal to 0. So it's basically the same argument that I made a minute ago. Okay. But here's the thing now. I know this, right? If V is in V, then V transpose AV is less than or equal to 0. I know this. If U is in U, and U is not 0, then U transpose AU is positive. Okay? So what's the intersection of U and V? Well, they're subspaces, and so that means that both of them contain 0. So 0 is in U, 0 is in V. That's in the intersection. Can anything else be in the intersection? No, because if you had some non-zero vector that is both in U and in V, then by the virtue of being in U, you would have X transpose AX positive, and by virtue of being in V, you would have X transpose AX be negative. Okay. So from these two statements, it follows that U intersect V is just the origin. Okay. Now, again, remember, what am I trying to do? I'm trying to prove that V actually is nothing, that V is just the origin, right? And so what I want to prove is that actually this K is so small that it's actually 0. So I'm trying to prove V is small. And this is a very good step because I know that U is very large. U is a n-1 dimensional thing. Okay. So it's a hyperplane, actually. And so V is some subspace which only intersects that hyperplane on one point. So how big can this dimension be? It can be 1 at most. Because if it was 2, then these guys would intersect in a line at least. Okay. So I conclude that this thing has dimension less than or equal to 1. Almost, right? I want it to be 0. but I proved that it's 1 at most. Okay. Dimension less than or equal to 1. Okay. So it follows that A has how many positive eigenvalues? Well, all except maybe 1. Okay. So A has either 0 or 1 eigenvalue less than or equal to 0, which is almost what I want. I wanted to have no eigenvalues less than or equal to 0. Okay. Why am I not done? I'm almost done. Well, let's go back and see what we've used. I started by assuming that the principal minors of A were positive. Then I used that to conclude that the principal minors of A prime were positive. And then using that, I made this whole argument. Okay? But in going from here to here, I threw out one minor, the biggest minor. Yeah? In going from here to here, I'm forgetting that the determinant of A is also positive. If you think about it, that's going to do it. Yeah? The determinant of A was also positive. Right? What's the determinant of A? It's the product of the eigenvalues. Now, we're saying that there's either 0 or 1 non-positive ones. Well, you see, if this product is positive, first of all, that means that it can't be any zeros. And second of all, it means that the number of negative things is even. So the number of negative eigenvalues is even, but it's between 0 and 1, so it's 0. And that means that all lambda i's are positive, which means that A is positive definite, as we wanted to show. So that's the proof. That's the proof of Sylvester's criterion for positive definiteness. I like this proof. It's a good proof. Now, let me give you a hint of what's next then. Again, W is finite if and only if my bilinear form is positive definite. Okay? And so how are we going to figure out which are the finite Coxeter groups? We're going to figure out when these matrices, so we're given this thing, right? And it's controlled by these numbers mij, which are the exponents of Si, Sj. Now, this positive definite bilinear form basically defines for me a matrix of the form minus cosine of pi over m11 minus cosine of pi over m12 until minus cosine of pi over m1n. Now, this is symmetric, right? Because mij is equal to mji, so you get the same numbers here. Here you get minus cosine of pi over m22. So we get this matrix. This is a representing matrix of this positive definite of this positive definite form. And so what we need to understand now is what are the values of mij that make this matrix positive definite. Now there's different approaches for doing this, but the approach that I'm going to use is Sylvester's approach. Sylvester tells you that this matrix is positive definite if and only if when you compute the principal minors of this thing, they're all positive. So we're actually going to be computing a bunch of determinants and proving that they're positive. Now, if you look at this, this should look to you like the last matrix whose determinant you want to compute. Right? But if you think about it, the situation is not so bad because most of the MIJs are infinite. Are 2, rather. Sorry. In a Coxeter group, there's very few edges. Generally, the diagrams that we've seen have very few edges, and most of the vertices are not joined by an edge, which means Mij is 2, which means minus cosine of pi over 2 is 0. And so really, when you look at this matrix, it's mostly zeros. And that's what's going to allow us to compute it, and that's what makes this a feasible approach. So what we're going to be doing is this kind of computation. So we'll do that next time.
I'm not sure, but I can look it up. I think I just looked up on Google positive definite principal minor.
Okay.
But I can look it up and I'll
Yeah,
send it to you.
And is it less than 5 years old or more than 5 years old?
More.
More, good, okay. See what I'm getting at, I want to do something in class that I have never, I want to do something unrehearsed in class. So what you're telling me is that a search on JSTOR for the terms here would turn up that article. That article may refer to Sylvester or it may not. If it doesn't refer to Sylvester's article, then I would have to go back to through the German reviews of that time to figure out which article.
I see.
But the titles are in English, you see. So.
Yeah. I assume that it should be, I mean, they should have a reference to Sylvester because the monthly is very strict about these